Okay, so we are going to touch on the final review right now. And then if you have any questions, let me know. Okay, so check out your Canvas. There is the final review module that I have placed on Canvas. And then I will post the videos after. So hopefully we'll be able to finish it all today. If we don't, then we'll carry it until next Tuesday. I will give you Thursday to work on your project. Okay, so first thing first, I'm going to go over the final review part 1. You can find this in your assignment or on the module. Okay, so if you click modules, scroll down to after quiz. Okay, so for this week, since we don't have any additional lecture, there is a quiz review and a third quiz. Make sure that you address that by Sunday, work on your project, and then we're going to go over the final review now. Okay. All right. So I am addressing part 1 of the final review. And part 1 covers chapter 1 through 6. That was the first half of the semester. Okay. So for number 1, we're asked to convert the binary, the decimal 205 to the binary. Now on the final exam, you will be required to use the lockdown browser. That means that you will be provided a link when you click on the exam to be able to download the browser. You cannot use any link. It has to be linked to the exam and for the license of the instructor. So I will also release password that day. Maybe I won't use password, we'll see. But on that week, you can click the link, download the lockdown browser. Then you would use the lockdown browser to log into Canvas and then access your exam. It will not let you take exam with regular browser, and it should be compatible with all systems now that they have developed it for Mac OS, PC, and even Chromebook. But if you have any challenges, you can also borrow a laptop from the school. Make sure you do that earlier in the week. The final will be open first thing on Monday for the final week, and it will close on Thursday of that week for this class. Okay. All right. So the first question asks you to change 205 in decimal into the binary equivalents. You will not be allowed to use programmer computer calculator on the PC that you're taking the test with, or the computer that you're taking the test with. So make sure that you know how to do this manually. So if we convert this, we can go through the subtraction method, where we would put out the scale, multiple of 2, because it's 2 to the power of n for the binary equivalents. And then we would take 205, subtract the largest value at the decimal bit, and then go from left to right. And so our most right is going to be the least significant bit. So this is the answer for number 1. Make sure you know how to do the conversion. For number 2, you will also be asked something similar to this on the final, where you are given a hexadecimal value and you need to convert it into binary. And we know that each of the hexadecimal is equivalent to 4 bits. So a 4 is a 4 in decimal. So we simply convert that as 0100. The E is 14 in decimal. So we would take 14 and convert it into binary. And then 2 is a 2. So 2 in hex is 2 in decimal. So we would convert that into binary as 0010. And then the C is a 12 in decimal, and we can convert that into binary as 1100. So as you put it all together, each digit is equivalent to 4 bits. So when you combine them, right, the 4 is here, and then next to it is going to be the E, and so on. So this is the binary equivalent for this value in hex. So make sure that we know how to do that, and that's the simplest way. Then you're asked to find the 2's complement for the hexadecimal 8A2. And in the question, it's going to tell you that this is going to be a word size storage. That means that it is 16 bits. So we have to fill it out to the 16 bits. Okay. So first, the first step is to convert this hexadecimal to a binary. Now you can use the complement, the 2 complement for hexadecimal. That's fine too. But I found that the easiest is to make this into binary. Just like what we did in number 2, we take each of the digit and convert it as a 4-bit binary. So 8 is equal to 1000. The A is 10 in decimal. We have 1010. The 2, least significant bit, that's going to be 0010. So as we write it out, it will be like this. So once I have it in binary, then I would apply the not operator or 1's complement. So I would flip the bits. The 1 becomes the 0 and the 0 becomes the 1. So at the 1's complement, I have this. We're not done. So the last step will be adding the 1 for the 2's complement. So we would add the 1 to this. So as you add the 1, you would have a carry. And so since I have a carry, and then I would have the 0 here, because 1 plus 1 is 0 with the carry 1, and then 1 plus 0 is 1. So this is our 2's complement binary value. Now, once I have that, notice that I keep it in the 4 bits chunk so I can convert it back into hex. So the first 4 is going to represent 7 in hexadecimal. The next 4 bits is going to be the 5. So you simply add, you would simply put this on the scale and then be able to add the value that has the 1s on top. Okay. So I would have a 5 for the next 4 bits. And then lastly, on the most right 4 bits, that's going to be 14 or E in hexadecimal. So once I'm done with the binary 2's complement, because the question asks for hexadecimal, I can convert it back. Now, if you know how to find the 2's complement using hexadecimal, you're welcome to do that. I think we did practice with that as well. So the final answer for number 3 is F75E. Why do I have an F? Because I need to fill it out to the word size. So that means that the bits in the digit in the front needs to be F to indicate that it is a sign value. Okay. So here I put that F signifies the negative value or the sign value. So don't forget that it is a sign value because you went from positive to the negative. So you got to make sure that that F goes in the front. And if you double check when you do your assignment, you can look at your programmer calculator. But again, for the test, you will not be allowed to use programmer calculator. Any question? Okay, next, you're going to have additional practice with the 2's complement for number 4. So I'll move this down a little bit. So here we have a decimal value, 811 or 811 in decimal. We want to convert this into binary. So you can go two ways. You can do the division method or you can do the subtraction method. Ultimately, you will get the same result. So I can go down the scale and start subtracting the largest value if I'm using the subtraction method, or I can take 11 divided by 2. If I have a remainder, that's a 1. If I divide it evenly for the quotient, then I have a 0. So after I convert that to binary, I would have this value. Then I would go to the next step where I apply the not operator for the ones complement. So I would flip the bits. The 0 becomes the 1 and the 1s becomes the 0. After I have completed the 1's complement, I would then simply add 1 for the 2's complement, which gives me this, right? So when I add a 1 to this, I would have the 1, so the 1 drops in and everything else stays the same. So now I would have the binary result for the 2's complement for number 4. And it asks you for the binary. Okay. So make sure that we know how to do 2's complement in different number system, hexadecimal, binary, and decimal. Ultimately, I think getting it to the binary is the easiest approach because we have to flip the bits, or if you have hexadecimal, you can use 2's complement for hexadecimal. Any question? Now for the answer, you can simply type out the answer. I just give you the steps to help you review in case you forgot how to do it. So I wrote out the step, okay, but you don't have to for submission. Okay, so the next part, we're gonna work on binary arithmetic. So number 5, we are to solve the binary 111111001, add it with the second value here in binary. And just like how we talked about before, make sure we remember the rule. When you have a 1 plus a 1, you have a 0 with a carry 1. And you would handle 2 number at a time, right? You add at 2 level and then carry it down to the next level when you apply the carry. So as I do that, the first one right here on the right, this one plus with this one, you would get a 0, and then we would carry over here, and so on. So my result at the end, after I applied the carry, it would be that. Now the test is multiple choice. You will have different choices to pick from. So you just got to make sure that you select the right answer. So make sure you double check. You can use scratch paper, right? Make sure we have integrity in the test, in that, we should apply our knowledge and be able to answer instead of using a cheat sheet or something like that. Okay. Then for number 6, again, we're going to do subtraction. So when we have to think about how the carry rule will be applied. So when you take a 0, subtract a 1, you have to also apply the carry. Okay. So when we take this value, subtract with this value, a 1 subtract a 1, you get a 0. A 1 subtract a 0, you get a 1. A 0 subtract a 1, you get a 1 with a carry. So you bring that over to the next column on the left, and you would apply, or we would say borrow, carry is the same. So you borrow from the left side, and then you would apply the borrow accordingly. So the final result is this. So when I write it like this, all that means is whatever in the front for the rest of this is going to be this 0, 0, 0. Okay, 1, 2, 3, 4, 5. Yep.
Couldn't we just add it and then use the 2's complement?
You would. So the proper way is to do the 2's complement of this and add it. That's more appropriate. So you would do this, add it with the 2 complement of this. Understand? Because you're subtracting the second part. This is what you're subtracting. So if you flip the bits and add the 1 to this and then add it back to here, that's the correct way. Because if you add this up and sum it, it's a sum of these 2 value negative. That's not right. Yeah, so what you can do, the easiest way in your approach is to flip the bits for this plus 1, make it a 2's complement, and then add it back to this. And you should still get the same result. It's like adding the negative of this, right?
Okay.
Yep. Other questions? Okay. So this just gives you some practice. You're going to see similar question to this, right? For number 7, we are going to apply the OR operator, right? Anytime with the OR, anytime you have a 1 in the mix, you're going to get a 1 as a result. Okay. So a 1 or a 1, you get a 1, a 1 or a 0, you get a 1. So just remember that rule and you're good. Okay, a 0 or a 0 is a 0, of course. Okay, so make sure that we know our operators. And then, so for 8, you are going to have not and. So the way that we handle NAND is we are going to AND it first, get the result, and then not it. Just the same as NOR, right? We would OR it first and then not. So it's a 2-step with this operator. So I would first take the first value, AND it with the second value. So in the AND result, I would have this. And for the AND rule, anytime that you have a 0 in the mix, you get a 0 as the output. So a 0 and a 1, I have a 0. A 1 and a 1, I have a 1. A 0 and a 1, I have a 0. So once I have the AND result, then I would NOT it. So that way it will become NAND. So that simply flip the bits, right? This is going to be your output for NAND. Okay. Question. The reason why we AND first is because AND requires 2 input. So we have 2 input here. So we have end up with 1 result for after we AND it. NOT requires only 1 input. So you would apply NOT after you applied the AND. Okay. All right. Question. Okay. There will be some concept-based questions. So number 20, the type of architecture under ISA classification directly uses the memory instead of the register file to hold data and instructions. What type of architecture? What we're learning is complex instruction set computer. I'm sorry, we're learning RISC, but complex instruction set computer, CIS, architecture access memory directly. When we use RISC, which is what we're learning, we use register. So when you program, you use, register 1, R1, R2, R3, and so on. That's under RISC, RISC architecture. So when they ask you, what did you learn in assembly programming? You can say that you learn how to program RISC architecture. And we use register file. So when an architecture that doesn't use register file, it access memory directly. That's a different architecture. So every processor, even the same brand, the model can be different. Okay, so usually Most of the time manufactured, they would produce RISC architecture because it's fastest to produce. It uses simple instructions. There are many benefits in RISC versus CIS. Okay. Number 10, which architecture requires more complex hardware to implement instructions, which are generally register-to-register operations? That's us, RISC, in this class. Reduced instruction set computer. It relies heavily on the actual physical hardware to implement instructions. So, and because of this, right, when we already have, it's either software or hardware. So if it's rely heavily on the hardware, our instructions would be more simple. So make sure we know the differences. Any questions with 9, 10 or prior? All right. Directive for number 11, directive is a built up from discrete statements or instructions that requires particular registers for arithmetic, addressing, or control functions. Memory locations or offsets, address modes used to interpret the operands. False. It's machine language. Okay. Machine language is built up from discrete statements or instructions. And in this class, when we write instructions for our system, it breaks it down to what we call machine language. Okay. Now, the questions on the test will not be exact like this. It might be a multiple choice question. It might be a fill in the blank, giving you the choices to select. Okay, so make sure that we understand what machine language is. And then we talked about N-type and P-type in the earlier chapters. So number 12, what type of MOS transistor pulls voltage up when it receives 0 inputs? And that will be your P-type transistor. And P-type pulls the voltage up when it receives the 0. And this is what is implemented in the gates for your logical operator, and or NAND, XO, exclusive OR, and so on. The N-type and the P-type. So P-type, it pulls the voltage up when the input is 0. So make sure we know the difference between the N-type and the P-type. For 13, what type of sequential circuit systems coordinate signals and control data movement? That is your state machine. It coordinates signal and data movement. So a state machine simply represents how the system can be, it retains its state. Like what you install on your computer remains when you turn the computer off. Okay. So with that, it would require data, which comes from after you install the applications, right? That would require some storage. And also signals to be able to retain the data. For 14, fill in the blank. A circuit that changes a code into a set of signal is known as a decoder. So the decoder is a circuit that changes the code into signals. So as you know that we are using, right, your computer system is made of circuits. So it would require a decoder to convert everything to a signal. Or a group of signals, or signals I should say. 15, what type of circuits is used to trigger transitions from one state to another in a state machine? It is the clock circuit. it triggers transition from one state to another. A clock circuit. Okay, so make sure we know what a clock circuit is, a decoder, what is a state machine. 16, we did this in our assignment where we talked about how we would represent multiple bits in a word, right? We would denote it from left to right. So for the highlighted, we are looking at bit 15 because here is the least significant 0 to 15. That's our 16-bit word size. So 15 to 11, just for the yellow highlight. And that is equivalent to this. And before we went into the instructions, we have to learn how to look at multi-bit representation as the instruction is broken into different sub pieces that would represent certain type of operation like add and not and so on. Okay. Usually your operands are like the 4 bits in the front, so 15 to 12. Okay. For 17, fill in the blank. A transistor that performs the basic logical function and considered to be the fundamental building blocks of the digital integrated circuits is a logic gate. A logic gate. Okay. We talked about gate and how gate is used in our logical operators and in computation. So this is what we see with and, or, not, and so on. Any question? Okay. Let me move this up. I don't know why it came all the way so far down. Maybe I did modify it before. Okay. So for 18, the differences between combinational and sequential circuits. Make sure we know the difference. A combination circuit provide the same output given the set of input. It is stateless. Sequential circuit, it stores information in which represent its state. So the state is used for the output, therefore it is stateful. Okay, so combination circuits is stateless and sequential circuit is stateful. And sequential circuits store information or state. Okay. Any question? For 19, you will be given an image for the gates and you have to know what that is, right? Okay, so we can distinguish. So now let me move this one down a little bit more. Any question with 17 or 18? Okay. We've seen this before on assignment and quiz and so on. So for A, for 19, right? It asks you which of the following logic gates represents not and or NAND. So for the first one, option A is a NOR. Okay. When you see the sharper arrow like this with a bubble, this bubble is not right? So we OR it and then not it, so NOR. For the AND, how I remember it, it's shaped like a D. So, and then since it has a bubble, that will be a not AND. So your option B is the correct option. Now for option C, it is just an AND. We don't have a bubble, so it's just an AND. So C is incorrect. So B is your answer for 19. Any question? Okay, I believe unit 2 went over this. For 20, make sure we know what a mux or multiplexer is. So in a combinational circuit of a processor, what component permits input and output selection? And then that is a multiplexer. And simply a multiplexer is a group of logical gates, which go back to the first part of the question. It is a combinational circuit. For 21, which assembly operation writes the value to the memory location? And remember this, when you do stacks for your project, you store. So store writes the value to the memory location. We would use ST, STI, or STR. STR is used register to register. STI, we can use register to a label. ST, we would use a register to a label. Difference between ST and STI in that STI is indirect and ST is direct. For 22, in a processor, which component is considered as a small temporary storage of the processing unit? And that will be your register. It is a temporary storage of a processing unit. In LC3, we use this register 0 to 7, 8 general register. Now, other assembly programming languages would use more than 8 registers. Some would have 15 or 16. Okay, but in general, your register file is the same. It's used as temporary storage. Nothing retains there when after the program is run for good, right? Sometimes you see values there, but we don't really use register to store things permanently. 23, in an addressing mode, where can an operand be found? In 3 areas: in memory, in register, and in the instruction. Make sure we know those locations: memory, register, or instruction. 24, identify the operational instruction in LC3. There are 3 operational instructions in LC3. So when you operate, you use these: add, and, not. 3. Now, other languages use more, right? Like OR and so on. But in LC3, to keep it simple, we simply add, right? And then and not, and use mostly for clear, right? Not, we can use it for complements. Or the opposite, we would apply the opposite of that, right? So we only need those 3 for operation in LC3. 25, what are the conditional codes of LC3? And you see this in branching when we would apply branch for conditional statement like if, else. So negative for n, p is for positive, z is for 0. These are used to indicate the condition of which bit can be used by one of the control instructions to change the execution sequence. Because when you execute that based on the condition of that bit, right, it just changed how your program flow. It would go to a certain area of your code. So when we branch, we can go to a label or a section of our code. Any question regarding 21 through 25? Okay, 26. Which instruction stores the content of the source register onto the memory location, allowing the instruction to access full memory address space? So you have the STI, which is an indirect store mode. Okay, it uses the indirect mode. The content of the source register is stored onto the memory location. The content, what's inside that register, is going to be stored onto the memory location. So when we say STI R1 label 1, what's in R1 is going to be stored at the location that is name label 1. And label 1, we would fill that with, let's say, hex 3150. So we would go to hex 3150, right, to see the data for what was in register 1.
So quick question.
Yeah.
I probably already, no, you have already answered this, but how would the statement of that question change if the answer were ST, like the direct ST?
So the direct ST, the address mode is applied. Okay. So in your processor, because you have the arithmetic unit and then the control unit, there is some part of it is not loaded. So your address mode is not loaded to a certain location for the processor in STI compared to an ST. Okay, because when you use an STI R1 label 1, the address for the label 1 is brought into the ADR. That's how it's able to simply access that exact location to store the content of R1. Now in the ST, it directly accessed the location period. It doesn't. So think of SCI as we use a pointer to point to an address. That's the simplest way that I can put it for you. Okay, it's pointed to the address versus the access the address directly in the direct store. Okay, so you use a location to point to another location. So you use an address to point to another address in an STI.
Okay, so like if I were using an STI, I could point it to, let's say, X3150 or whatever location. And if I'm using an ST, I could just say, okay, let's put this directly into the label, kind of.
Right. So even when you fill the label hex 3150, right? In an ST, the processor accessed hex 3150 directly. In an STI, it uses a location, which is where your address is. Think of it like an address pointer. It points to a location. So we're using a memory location pointing to another memory location. So in an STI, it's an indirect access, meaning that I have to say, oh, go here and then go there. Okay. So efficiency wise, not a huge difference. You still achieve the same thing. But, if you think about like resources, yeah, ST is probably a better way to go. But, if you want to use location to access another location, you would use STI.
Okay, makes sense.
Mhm. For 27, write the instruction to load the address hex 3105 from the label ADD1 onto register 1 without accessing the memory. Okay. So the key word here is without accessing the memory. Okay. Now we can load effective address. Okay, so that's a little different than your LD and LDI. We touch on this in several chapters, right? So what I can do is I can fill my label ADD1 with the address hex 3105, the actual location. And then I can do a load effective address register 1. Why can't I do an LD here, right? It's not accessing the memory. An LD, it access memory. I cannot use LDI here because LDI access a memory to access another memory. It's a two-step. Okay. So when you load without accessing the memory, you would do an LEA, load effective address. You bring the address directly into the register. So this goes here. Okay. Question. All right. So we went over exercise like this. By this time, we should be able to break down your variable to pieces. Okay. So let's do 28 together. We want to calculate z is x minus y, and x is 9 and y is 5. That's easy, right? Algebraically, we would then plug 9 in for x, subtract y, which is 5, so xz should be 4, right? You can solve that quickly with math, but now if we can write a program to do that, right? So origination address to start for Lc3 or assembly. We would load the label X. So I'm trying to get this equation into the program. So my variable needs to get loaded, right? So you initialize your variable X and Y here. And I used register 1 and register 2. So I did an LDIR1X, LDIR2X. Can you use an LD? Sure. Okay, if you use an LD, you store with an ST. Okay, then I clear out register 1 because basically here at this point I would have, x is equal to 0, right? And so after I clear out register 1, I add 9 to register 1. So now x is 9. Then I clear register 2. Same thing. So now my y is 0. Then I add 5 to my register 2. So that now my y is 5. Because we are subtracting y, we got to do the 2's complement of y. Can I add -5 here? Sure, right? We would save a couple of steps, but in the technicality, right, the proper way is to add the 5 and then we do the 2's complement to represent negate y. So here we would negate, so we did the not to flip the bit, add the 1 for the 2's complement. So now y is -5 in R2, register 2. Then we combine them together by adding. So we would add, right, the x with the -y, and we put it back onto register 1. So now we need to store it to the label z because our output should be at z, right, the location. So we would store it because I use LDI here. I use STI at the end. So we store it to register 1. And then at the end, we simply fill the location for our variables X, Y, and Z. And we end the program. Can you add a halt in here? Sure, you can at the end to stop. Okay. Any question? So you will be expected to understand or be able to, to understand snippets of LC3 on the test. You will be given pieces of the program and it will ask you like, you know, what is Y at this stage or so on. Okay. Now at the university for this class, right, they have you write out your code in the final. I'm not going to be cool and unusual. We already do that for our project. So, okay, 29. Systematic decomposition. Make sure we know the definition for that. It is a way to break down your problem into subtasks. So we would decompose each of the subtasks into the smaller subtasks and so on. So that way it would become a machine instruction level. So when you pseudocode out your project, right, you need to break it down to the simplest level for all the procedure that you want to accomplish in your program. And at the lowest level, you would be able to put in your assembly code. Okay. Systematic decomposition. For 30, LC3 instruction that has no limitation on where the next instruction to be executed must reside. We do a jump, JMP. And it's the same for all assembly language jump. Sometime it will be jump spell out, sometime it will be JMP, but it just indicate that it would go to that section regardless. So we jump to a label. Okay, so I can say jump loop, right? So it will go to, now, ideally when you're using a loop, you would do an unconditional branch because it's you know, for iterative. So you would branch it back to the beginning. Like if I'm doing a while loop, I just do an unconditional branch back or a do while, right? You learned that in C and C++. But if you want to send it to a certain section, you can jump. Okay, and remember we talked about register 7 with jump. Okay, for 31, we need to know the binary equivalent for the opcode. So when you get 0001 in the first 4 bits, when the computer sees that, it understands that it is an add instruction or operand. Your opcode is 0101, that is an and then the not is 1001. Okay. We went over this, we fill out our little instructions. And then for the LDR, it's 0110. So in variation of the first 4 bits, you would have these instructions. Okay. So that the processor, it was programmed to understand that these bits mean these opcodes. Okay, for our architecture. For E, when you have 1011, that is an STI. And remember that everything is broken down to the binary. So when you write like load, not, and, or, right? Oh, I'm sorry, no, load, and not, and add, right? These are the binary that would be used, okay, for your opcode. 32. We need to know trap vector. I think I've been saying this for like many chapters now, because since halfway through, we start learning about trap vector already, okay, until the end, or mostly the end. And you've had charts in your notes and in labs in various parts that talked about trap vector. So we need to identify the appropriate trap vector for our pseudo instruction. For your in, for input, in is used for one character input. Okay, in LC3, you know, you can't have a string input. So simply, if you want a string to be input, you just have multiple inputs of a character. So like, let's say if you want to ask the user to input their first name, it's just multiple inputs of the group of characters that would represent their first name. So in is a trap vector, hex vector 23. So trap vector 23. When you halt, vector 25. When you do puts, it points to register 0. I'm sorry, pointed by register 0 for the display. That will be vector 22. Get C is different than in that it gets a character from the keyboard. That will be get C, and that's trap vector 20. Okay. Any questions with these? You can check out and so on. Okay, that would take care of part 1. I have time, so I'm going to try to do part 2 and the code piece. Okay, so there's a third piece to it. So that way, you know, you don't have to log on next Tuesday. You can, if you have question, to go through the final review. Okay. Any question regarding part 1, chapter 1 through 6? All right, so let me close this, and I'm just going to save my file real quick.
Professor, I do have a really quick question.
Yeah.
For question 10, when we covered the risk, if I'm not mistaken, did you mention that R stands for register?
Oh, reduce instruction set.
Oh, it's reduce. Okay. And then for the CIS, is that where like Cisco comes from, like the certification and things like that? Is that what that is?
No, it's for
okay.
C stands for complex instruction set. Cisco is just their name that they chose for the company.
Oh, okay.
But yeah, so when you, so these acronyms, right? Your complex instruction set, right? CISC, right? These are the acronyms.
Okay.
Yeah, so that's just an architecture family for a certain type of processor. So when you look at like the processor for your iMac or your MacBook or your PC, like AMD, Intel, and so on, they would fall into a category or a family of processor, right? So in general, like your Snapdragon and your iPhone processor, it would be under the risk. So we devote more time because technology is abundantly available for us to produce hardware that would reduce the instruction set to something more simple where it would be able to, this is why we're able to have, you know, less on the software, more on the hardware, but make it faster and simpler.
Okay. All right. Thanks for explaining that.
Yep, no problem. Other questions? Okay.
Professor,
Yes.
can I see number 1 again?
Sure.
Thank you.
You're welcome. So 1 just for binary conversion from decimal. Other questions? Okay, so next piece, part 2. You can download part 2 from Canvas. This is from chapter 6 through 19, and then we have a code part 3. Okay, and if you're done with everything, you can submit it today, or just remember to do it by the due date. But use it to review. That's why it's this thing. I want to implement this so it'll help you. Okay. Okay. What is an instruction in computing? It is a fundamental unit of work. Okay. And that could be operation, or it could be movement for data. So ultimately, it's a fundamental unit of work. Make sure we know the definition. There are 3 categories of instructions. We have computational, which is an add, data movement, load, store, control instruction, jump, branch. Okay. In general, you would see these categories the same in other languages, like Microsoft ASM, NASM, ARM, and so on. So these categories are used for their group of instructions. So in computational, for the others, you might have or more complex ones. But for LC3, we would have these categories as well. Okay. Then for 3, we would write an assembly program that set X at 32 hex 3200, Y is at location 3201, X is 4, Y is 3X. Okay. That's easy, right? You fancy, you can write a function with it, or a subroutine. Okay. So I'll just do the arithmetic. It's easy to break it down for the beginning part of the class anyway, or midway through. So origination address at hex 3000. We're going to load the variable. So we declare variable X, LDI R1X. And you can clear it at this point. So if I want, I can add another line. I can say N R1 0, right? Here at the next line here, I take 4 decimal and I add it to register 1 and put it on register 1. So your register 1, which is X, is going to be now initialized at decimal 4 or int 4. Then we load the second variable Y. So we declare Y here. So LDI R2Y. And so load Y into register 2. And in this one, I clear. So I N R2 0. So we clear register 2. That means here our Y is 0. Now, for your project, I don't want you to spend the time to comment every line. You need to comment the section of your code, right? So if you have a stack section, right, on stack, off stack, or push or pop, whatever, you comment that section, or your functions or your subroutine. Okay. All right. Clear R2. Then we are going to add, right, X. So what I did was I took X, which is in register 1. I added with register 1, which is another X, and I put it on R2. Because now here I would have Y is equal to 2X, right? Because R1 is an X and another R1 is another X, so that 2X. And then I store it, I put the result in register 2, which is Y. And then I simply add another register 1 to my bad. This should be R2 right here. Okay. So I take the 2x and I add it with another x to give it 3x and put it back onto register 2. Okay, then I copy it to register 0. Now it tells me to display the value of y. That's why I have to move it to register 0. So I copy it to register 0. And then I need to do Ascii conversion. I know you love Ascii conversion so much. Okay. So I didn't put the code here before the put, but what you can do is you would need to take register 0 and you need to add the offset. So for example, I'm going to do a couple here for you. Add R0, R0. And now if you're using a decimal, you would need to do 15, right? Add R0, R0 with another 15, and then add R0, R0 with a 3, right? That gives, oh, I'm missing another one to give it 45, just, or you can use a label, or you can use hexadecimal, which is 30. So all of this together, what we did was we offset it, right, for Ascii to decimal 48. So when I have a 0, right, it is the difference between a 0 and Ascii to the decimal is 48. And then if I use a hexadecimal, the offset is 30 in hex. Then now, since I already have it on register 0, then I can do a put, display on console, then I can halt. Then I would fill because the location was required at the beginning. So we would fill X at 3200. That's where your input's gonna be, right? Where you would set the value. And then you run the program and then you go to 3201 to check what your Y would be. So if I set my X is 2, then I should have Y is 6 in decimal. Okay. Now this program didn't have the user input. We manually hard code in the value and then we simply convert it to output. Okay. Question. Okay. So make sure we know how to read this program or write a simple program. All right, let's go to the next one. So we're using Lc3 to write a program. We have A plus 4 is greater than B. A is at location hex 3100. B is at location hex 3101. Okay, origination address at the beginning at hex 3000. We now going to declare a variable. We're going to load A to register 1. Then we initialize 4. Okay. So here, I'm sorry, not initialize. We're going to add 4 to register 1. So that's going to represent A plus 4. And then we're going to put it on to register 1. So your R1 has A plus 4. Then we declare B. So B, load it to register 2. And the way I approach this is I did the algebraic move. Okay. What you can do is if you already have, this is register 1, you just have to compare it to register 2. Okay. So you simply, I'm gonna hold on, don't write this down yet, right? So I'm gonna do the branch comparison for you exactly like this and not do the algebraic. Okay. So after I load the register for B, I need to represent this is greater than this. So how can I do that? If I take this and subtract this, right? I can check for positive, right? So if I take A plus 4, subtract B, if I move B over to this side, right, it has to be greater than 0. So I had it. Oops. You don't want Python there. Sorry. Okay. Then I would have it positive on this side, right? So it's like this. A plus 4 minus B is greater than, oops, 0. So if I take register 1, subtract register 2, I just need to branch for positive. Okay, so that's what I did here. So first, I need to flip the bits for register 2 as the 1's complement. So I knot it here. Then I have the 2's complement where I add the 1. So at this point, my R2 is negative B. Then I add it with R1 and put it on register 3. Can I put it on register 1? I sure can. I just wanted to put on another register. So we would have R3 is A plus 4 minus B. So I take A plus 4 plus minus B and put it on register 3. Then now I can check for if this piece is a positive, right? So I simply branch positive and I send it to a label called comp to compare. Then in that label, I simply store it back because I load at the beginning. I would now store it to the A so I can check my answer, right? So store register 1 to A, register 2 to B, and then I would do a halt. And then after that, we can just fill. So fill A at 3100, fill B as hex 3101. And then if you really want to fill something else, you can, but actually, you don't need this. I don't need the comp there. It's just a label. Sorry. I don't know why I put that, but yeah, and so we can do a halt here. Oops. Oh, we did do a halt up there already. So after the fill, just dot n. Done. So that's how you can do branch comparison. Okay. Question? Okay, for 5, we need to put down the comment for the instruction, right? So for A, we would add register 0 with a 0 and put it on register 3. So when you see an add like this, a register with a 0 and put it onto another register as for the result, then that's a copy. So we copy the content of register 0 to register 3. For B, okay, this, I don't think I did. Well, this is going to overflow. So there's an error on here. This should be 15, 15, 15. I'm going to correct it so that way when you do it right. Okay, sorry about that. Add R3, R3, and then with the decimal negative. -3. So here we are subtracting. Check 3 from R3 starting R3, and this is, it should be 15. Yeah, because 16, that's going to bleed into the bit 4, so you can't, it's going to overflow because they're only, I'm sorry, bit 6. So there are only 5 bits that you can use for the immediate value. Okay. So when you have an input, the first part is to subtract it, right? Subtract it from the ASCII input so you can have the actual value, then you can compute it. And then before you output it, you add it back. Okay. So I put down that to convert values for register 3 from ASCII to hex by subtracting decimal 48. And we would do it in 4 instructions. Okay, so that's V, ASCII conversion from the input. For C, right, you have a label called begin, and you would have an LEA R0 prompt. So we load effective address of prompt to register 0. We display onto console, so we do a put, right? Like your prompt could be enter a number, right? So which is what it is. And then get C is to record input character. And then when we add register 0 with 0 and put it on register 1, we copy what was input from register 0 to register 1. So that's how we can move the input to another register and then keep asking for them to input more, right? Or they might have multiple inputs for their names or multiple numbers. And then for your prompt, because it's a strings, you would do a dot strings, and then you would have the string declaration with no termination. So enter the first number. So ultimately, if I comment this section, I just simply put load effective address of string prompt or prompt user, right? Now, a little bit coming back to B, okay? If you're using hexadecimal here, you can do the X instead of the decimal like this, okay? We talked about this before. Check your earlier lab. We did it in hex, and then we did it in decimal this way. Okay, so several ways we can do it for the conversion. So hex is going to be 30, decimal is 48. And then this is how you load a string to prompt the user. Now, after you have an input from the user like this, you got to do the ASCII conversion. So here, right, you should do an ASCII conversion. And then the rest of your program, of course. Okay, so additional comments are there. Let's see, for D. Oops. Okay, we're good there. For D, we are going to copy content of register 3 to register 1. So I did copy R3 to R1. And then I do a branch 0. So it's going to check If R1 is 0, it's going to go to show. Okay. So if R1 is 0, we're going to branch to label show. Oops. For question 6, in LC3, what are opcodes? They are reserved symbols that correspond to the instructions, what the instruction is asking the computer to do. So a task for the computer or the processor. Your operands are your registers, right? Your numbers and your labels. So what's considered an operand? That will be who the computer is expected to do the opcode to, right? So if I look at, like, for example, I can say add R1 hex 0. Oh, let's see. R2 hex 0, right? These are the operands. Okay. And then if I do add R1, R2 hex 0 like this, this is the outcode. So your operands are registers, right? Source and destination registers, your numbers, which are immediate value. It could be hexadecimal or decimal. And then also your label. Like we can do an LDI, R1, label 1, like this. Okay, so these are your operands. Question 8, the purpose of the following opcodes. Okay, these are more on your directives. So your BLKW with the value 2, that is block write to allocate 2 words of the storage, 2 times 16 bits. Okay, so basically you set up number of words by using block write like this. You can do 1, you can do 2, you can do many there. Okay. Fill and address that allocate 1 word initialized with the value this to represent location. So fill is exactly that, right? It puts that value to that label. See that strings, this is a string. You would count up the character here. Since there are 13 characters, that means that it's going to allocate 13 plus 1 locations and 1 character per location or word, initialized with the characters and no terminator. So it creates 14 locations for that string. And then a 9, once again, we looked at trap vector, a little different than the other ones. So your halt is vector 25, your out is vector 21, your puts is vector 22, and again, in is vector 23. Get C should be vector 20. So make sure we know them Any question? Okay. Let me move this down to the next one in case you're still recording the answer for 9. Okay, 10. The basic constructs of LC3 programming: sequential, conditional, and iterative. Sequential is when instructions flow from one to the next, top to bottom. No special instruction is needed to go from one to the next task. For conditional and iterative, your code is using conditions at n for negative, z for 0, and p for positive, where it applied the conditional branching or condition for the bits. Okay. In the for loop, we do that. In our while loop, we do that, and so on. So in looping or iterative, you have that. If else, we also apply that. So with conditional. And so we would use branch. For 11, what are the steps in debugging? We make sure we know these 3. Examine the sequence of the instructions being executed. We're going to keep track of the results being produced, especially for us with the registers, right? Compare the results from each instruction, then expected result. Okay. So you can step over the program. You can also check line by line, manually double check the content of your storage, like your register, or if you put it on stack, what is push or pop from the stack. And then coming to the later part of the book or our units, the type of files that are generated in Windows system when we build or assemble our program. So when you write the code, you save it as an .asm. Okay, that will be your assembly language program. So all assembly programs save as a .asm. Okay, some require special extension like NASM or MASM, but ultimately it is ASM for assembly. And because of that, we can use it with the assembler. So when your program is assembled, it creates 5 files. Your binary listing, which is .bin, your hex listing, which is .hex. This is mostly used for your simulator to show you what that hex equivalent is and what that the binary equivalent for instructions on your simulator is. Okay. Your object file, your OBJ, so you can load and run your program. The symbol table, we talked about this before, what goes into a symbol table. And then your listing file, .list. Question. 13, what does an object file contain? Your starting address, that's why we put origination at hex 3000, and in between, so your code, which are machine instructions. Okay. For 14, Describe the loading and linking in LC3 programming. Loading is a process of copying executable image onto the memory. So more when you work with assembly language, when you need to load some program where that will be using loaders to relocate the image that would fit into a certain memory size. And we also would link. So this is equivalent to import or include in C++, import in Java and Python, where we would use outside modules or libraries, right? STL. So we are linking the process of resolving symbol between different object files or independent object files. So you can have modular approach by using multiple object files and link them together. Now, if you do this for Microsoft ASM, NASM, or any C compiler based type of assembly, you would have to set up your C compiler IDE, hence Visual Studio, in the path to link the actual object file. Otherwise, even when you write .external, it does not know where to go. So if those of you who took Python or, especially Python, you got to bring down the packages and store that packages in the location of your Python directory for it to run. So that means you have to do, either git clone and then, or you can do a pip install. If you don't have the physical package or the module, the file, in this case, object file, it will not be able to see it, right? Because the computer, it's only going to do what you tell it to do. So when you're using this in assembly, make sure that that physical file is connected or linked to the location of your other object file, so that way you can run it. Because the way that the book says it, it just said, oh, this is notation would say .external. Even if you code that in .external in the path of the file, if you don't set up the link in your IDE, it would not build your assembly program. Okay, my experience with Microsoft ASM and other ASM that has been this way. So just keep in mind that when you do that for your executable or your object files. Okay, so the linker, what it would do is it's going to look for the symbol table for the other modules or files, right? Object file to resolve the symbols. So all the labels, all the things that's used in the other file, it's able to bring that into the symbol table so it would know, right? So when you say like import, I'm using GeoPy this week for my class, or some GeoIP too, where they do geolocation for system or the actual geolocation in Python, right? So when you say that, all the content of that module needs to be downloaded and installed so that way it can resolve, right? The classes, the objects, the methods that's used in those modules for your running script or your program. Okay, so logical, you have to think about how that would be interpreted in a logical sense. Okay, on linking external. Any question with load and linker? All right, 15. The purpose of control status register is that the CPU tells the device what to do. It's going to write to the control register. When the CPU checks if the task is done, it's going to read the status register. So the status is for it to check if it's done. And the control is for it to see if the device is doing it. It's like the processor is the parent, right? Use control to see if the kids are doing the chores, and then it would check on the status to see if the chores are done. Okay, 16, polling in ISA for IO management. CPU would keep checking the status register until the data arrives. So it keeps polling, or the device is ready for the next data. And the analogy the book uses, are we there yet? Are we there yet, right? So it keeps checking to see if there's new data or if the device is ready for data. The interrupt is that when the device sends a special signal to the CPU, when the new data arrives, or when the device is ready for the next data. So it raises its hand, right? And CPU can be performing other tasks instead of polling device, right? So it'll just say, you know, interrupt me when you're ready, or wake me when we get there. We talked about two types of register in keyboard and display. So make sure you know what they are and their addresses. Okay. Your keyboard data register, your KBDR, D stands for data. And your keyboard status register, KBSR. And for the KBDR, we use hex FEO202, that is, right? And for the status register for the keyboard, we use hex FE00. What is a stack? It is an abstract data type that is a storage mechanism defined by the operations performed on it. It is not at all by the specific manner in which it is implemented. It grows downward, and the operation would be last in, first out. Okay, push pop. So that brings us to number 20, part 2. Identify the operation to add or remove an item onto a stack or from a stack. You would push to add an item to the stack. We push an element onto a stack when we insert it. Pop, we remove an item from a stack. We would pop the element from the stack, and it would do, so the last thing that comes in is going to be the first thing that pops. The last thing that's pushed is going to be the first thing that's popped. Think about our coin, right, being pushed in, or a stack of plates. That helps me visualize it. So you stack your plates. Okay, the last one's going to be on top. That's going to be the first to get removed. A supervisor stack. Know what this is? This is a special region that is used as a stack for internal service routines. So LC3 saves the state information on a special stack. This is also a separate region of memory, not a regular stack. It's a supervisor stack. It's only used by the program to execute privilege mode, your system mode. Okay. (22) What does the activation record bookkeeping contain? I have a double K here. Oh, that's doing bookkeeping. We need that. Return value is going to be the space where values returned by the function. If the function does not return it, so there is that space. Return address. This is a save pointer for the next instruction in calling function. This is store register 7. So in the case that if we have a next jump subroutine or function call, it knows where to go for that subroutine. So basically it's an address for the next line in the instruction. Dynamic link is your caller's frame pointer. This is used to pop the activation record because as we return from the function, we're done with the parameters, the variables for the and all the components inside that function. We need to make sure that the activation record is popped up. So it is a frame pointer for the caller. To remove the activation record. So when should you save and restore register? This is expected in your project. You can. So literally in the code, right? We can do it as necessary, or you can do it at the beginning. So you just reserve that. You store it to that space. So we would do this when the values might be destroyed by the service routine, or when we need to use the value after that. So if you need it for the later part of your code or your program, we need to save and restore. Any questions with this? A stack pointer. So a stack is a sequence of memory location. Then your stack pointer is, its job is to keep track of the top of the stack. And I mentioned repeatedly, your R6 is your stack meter. So it's just a register where it keeps track of what's on top. And the location would contain the most recent element that's pushed. So my example for this is, say, let's say if I push 17, right? 17. Okay. If I push the 1 on first, it's at the bottom, right? And then the 7 on top. So the pointer now is going to point to the second value that's pushed, that's 7. So when I pop, I would pop the 7 first and then the 1. Okay. So it needs to track like which one is on top, on which elements are pushed. What occurs when there are too many items that are being pushed onto the stack? You have overflow. You can also have underflow if there's too few. So what causes an interrupt-driven I/O? So an interrupt is an unscripted subroutine call. It's triggered by an external element. And that could be device signals that needs to be serviced. Processor save state and start service routine. When it's done, the processor is going to restore that state and resume the program. So it's like this, right? A parent is busy doing something, that's a processor. A child is requiring attention, start crying. The parent's going to pause whatever he, she, they do, address the child's needs. So that means that the parent's going to pause and remember what they were doing, right? Address the child needs, so stop the child from crying, and then resume back when that's done. And that's for interrupt-driven I/O. Okay, so you have an external device signal that needs to be serviced. The processor is going to store its state so that way it can pick back up later, address the signal request, and then come back to the state and resume. Okay. Why should you use a stack? Because we only have so many registers. It is good for calling convention for subroutines. In the case that sometime you would call your subroutines many times, or you also have many subroutines in a program function or many functions. Algorithm naturally expressed in last in, first out with the data structure. So we would effectively use resource allocation this way for using storage in our processor. And I think this is recent. If you use the base address hex 31A0 to allocate one word per element, if you create the array, what is the address for the 10th element of the array? So you simply take the base address, which is hex 31A0, you add 10 because there's 0 to 9, okay? So there are 10 elements. So this is 0. Yeah, I'm wrong here. It should be 9. 9. Because the base is at your index 0 and it's going to go to the 10th element. Okay. Your 10th element, yeah, is index 9. So you would add the 9. So A9. Let me highlight this. I want to make sure I double check the final for that. Okay. I think we corrected that in the assignment too. So we can evaluate it, right? You would have hex 310 or A0, right, as index 0. Oops, I keep typing wrong. Okay. And then if we go to the next one, 31A1, right, which is your index 1. So if you count them up, 0 through 9 gives you 10 elements. So it's going to end up being at 9 for the 10th element. Just the way the question is worded, right? The 10th element is at the index 9. So you add the 9 as this is the base for the first index. Okay. All right. The base address is hex 31F0. Allocate the double word for each element. What is the base address for the 7th? So again, right, if this is this right here at the 0, we would go to the 7th element, which is at, so it's going to go to F0. F6. So this is your 7th element address right here, but because it's double, right, we're gonna multiply that by 2. So since double, we're gonna have a times 2. So here that should be 6 times 2. That should be at 12 A, B, C 10, 11, 12. So let's see. Also, I want to check this question. Okay, 30. How can you use pointers to obtain multiple results through the program? We would use arguments, and that is where we pass the address of the variable. So when you use that, for example, like I would have int function 1, and in the parentheses for C or C++, I would have int n, double price and so on. So when that happens, it passed the address of the variable int n. That's in your argument to where your result is stored. Okay. And so if you have multiple variables in the parameter, it would just use the address. So the return value would be via the pointer and or the status code for the function. So now you started to see that when we write programs, right, it's all about using storage and instructions, how to be able to pull data or put data in certain location and be able to calculate with the data. Okay. 31, recursive function is one that solves its task by calling itself on the smaller pieces of data. So recursive function calls itself. Example for this is running sum, Fibonacci, factorial, binary search, and many more. In C programming, the purpose of data structure is hence struct, group related items together so we can keep things in organization, organize these data bundles in a way where it's convenient for the program and it's efficient to execute. And we looked at some of the example like the flight, number, plane, and so on. And we want to establish an array that is one of a kind for the data structure or of the data structure. So what that is anything that is member in the struct goes into that array, which is a section of the memory that is allocating sequential addresses for the members. And for 34, we see the example here from the textbook. What is a struct in C? It is a mechanism to group related data items of different types together. So you can have different type group under the struct, which becomes a data type. "35, a linked list is an ordered collection of nodes, each of which contains some data and they're pointed sequentially to each other. So you would start with the beginning node, which is node 0, and you go to the end node, and the end node, it would be terminated. Now the doubly linked list, you would loop it, the end node, and point it back to the beginning node. Okay. Where it would be circular. This is used in data structure for C and C++. The advantages of a linked list It is dynamic in size. It can grow and shrink as needed. We can add new node by simply repoint. We can also remove nodes by remove the pointer and point it to something else. So you can redirect the link using pointer. So hopefully this class clarifies some stuff for you with data structure or C programming or C++. But if you haven't gone that far in the C++ classes, this will lead you to understand a little bit better now when you look at the higher level language program. Okay, and that's the point. This class is a harder class than most because we are thinking not just at the abstract level, but at the low level. Okay. All right, I got 9 minutes, so let me see if I can do it. Okay, questions on this? Let's see. We might go over a few minutes. Okay, number 1, part 3, assembly programming. These are just extra exercise that I want you to look at or do, so that way when you get the final questions, you would know what they are or be able to read the program. So I want to write a program that display the string I program in LC3. We've done this like in week 2. Okay. So if you're not sure, you can also look at the earlier lab. Origination address, we are going to do load effective address register 0. It's always going to use register 0 for LEA with the string, that is. Okay. So we're going to do a prompt. We're going to output that. So puts onto console, and then we halt. Because all we need to do is to display the string, right? So for the prompt, we simply strings, we fill that with the string and we put things in quotation marks. So that way we basically, this part is to declare your string value, and then we end the program. So that's how you can do equivalent to C out, I program in LC3. Then for 2, we would write an LC3 program that takes 2 inputs of decimal, which are integers, right? And display the sum of the input values. That's easy. Okay. So origination address at 3000, we're going to have 1 input for 1 integer. So that would be 1 character. And I would do a prompt for this. I got a little lazy, so I didn't do I did put a prompt for this. Yeah. So so I would take the integer, but remember it's in ASCII, so I need to like ASCII convert it. Now I use a label here, and for that label, I just fill it with a hex 30. So simply that's going to give me the conversion. Okay, so this is another approach. So I load register 3 with the label hex N48, and then I add whatever that offset is to the input from register 0 and put it back on register 0. I can skip a step by copying if I put it on register 1 here, right? But I want to show you that we can put it on register 0 and then copy it to register 1. So I can free up register 0. Then I have another in that will be the second input for the second integer. And I also then convert it to numbers by offset. Okay, because we already load once, we just need to add it here. And then I would add the integers. So then we prompt, so load L message to register 0 so we can output. Then since we have the input already, we're gonna copy it to register 2. Then we're gonna offset it for ASCII conversions to subtract 48 for decimal or text 30. Then we are going to add them together. So this is for ASCII conversion. This is to move it out of register 0 so we can free up register 0. And then we can output. Okay. Yep. So halt the program, your data section, you have the strings. Declare for the message, the sum of the number is hex and 48. We are gonna do negative. Hold on 1 second, okay. I'm going on 12 hours today, so sorry if my mind is like somewhere else. I only have about 2 minutes, but let me double check something. Okay, so. This is a little bit, so this, I want you to put negative x 30. Okay. This should be another label, but you can call it whatever you want there. Okay. So the hex offset is negative 30. For the subtraction, we got to add it back. So first, when you convert, you subtract the offset for the hex, and then you add it. Okay. Question? Okay, this is from the earlier lab, so. All right, we've done this in assignment. For 3, origination address. So we want to write a program that calculates R is equal to P minus Q. P is set at location 3200, Q is at 3201, and R is at 3202. So origination address to start, we're going to load the variable P. So I'm going to handle this and then this. Okay. Then I am going to, I'm missing, sorry. IR1 Q. So we got to load register 1 with Q. Then we're going to make the 2's complement to make it negative Q is equal to R1. Then we're going to store it to the, yeah, I don't know what I did with this one. Okay, so, all right, we're going to store register 1 to R because this is where I'm missing here. So let's do R2, R1, R0. That's more appropriate. So R2 is going to be P minus Q, which is R. Okay. Then we can store R2 to R and then halt. Have a chat. Okay, not a problem. Thank you. Okay, so is that okay? Any question with this number 3? So make sure we know how to write a program simple like this. Okay, so last one, number 4. Let's look at it. And you can practice, okay? So I'm just going over my solution, but you can write your own as well. So for 4, we are going to write Lc3 program. We have y minus x is greater than 0. Then z is y plus 2, else z is y minus 3. And we would put the location for x, y, z. X is at hex 3100, y is at hex 3101, and z is at hex 3102. Okay. So this one is similar to the earlier one where we do the comparison. So you have origination address. We're going to load the variable, load x to register 0, y to register 1, and z to register 2. Then we are going to set up the complement of negative x. So, I mean the complement of x, which is register 0. So I would do 1's complement for register 0, and then the 2's complement for register 0. So your R0 is negative x. Then we would take R0, add it with R1, so that would be y minus x, and our result would be at R2. Okay. Now here is where we finished there, and so we would need to branch it where it is positive, it is greater than 0 in R2, because this is less, 0 is less than x, y minus x. So we would do a branch positive, add 2. Okay. Else, we would do an add R3, R1, negative 3. Otherwise, we would take our y minus 3 and put it on register 3. Then we would store register 3 to z. So for the add 2 label, we simply take y plus 2 and put it on register 3, so we can store it as well. Okay. So z is going to be y plus 2 if this condition is met. Okay. If it's greater than 0. Then we store it from register 3 to z and then halt. And then our data. So let me move this up a little. Okay, so you just need to fill and dot in. Okay, sorry, I am 4 minutes over, but actually the class is going all the way up to like 8:10 or something like that on the schedule. However, I didn't give you a break. So the data section, just fill in the address that is found in the question, right? So that's where you're going to be go and find your input and your output. Okay, to test. And that concludes the final review, all 3 parts. Any question? Okay, stop recording.